Hello, my name is Fu, and today I'm going to be talking about Kepler's three laws of planetary motion. As an introduction, these laws were empirically um, derived by Kepler, Johannes Kepler, sometime like 14th or 15th century. I forgot actually. I should probably know that, but it's too late. I already started recording, so. What he observed in his empirical analysis of the celestial bodies from using a telescope, some basic observational equipment, is that each planet orbits in an ellipse. No, sorry. Each planet's orbit is an ellipse, with the star at one of the focuses of the ellipse. Secondly, the second law is that the amount of area swept out by the line that stretches from the star to the planets is always going to be equal, no matter the position of the planet in its orbit, if the time that you allow the planet to sweep out that area is always constant, which is visualized here. If the interval t2 is equal to the interval t1, then the area traced out will always be the same. And certainly we simply have this relationship that the period squared is proportional to um, the average distance of the planets from the sun, which is we can just also restate that as um, a cubed, where a is the semi-major axis of the planet's elliptical orbits. So I want to go over a rather detailed proof of all three of these laws. To do that, all we're going to need to know is some basic conservation laws of physics. So, you know, conservation of energy, conservation of angular momentum, basic properties of gravitational force, that it's center-seeking, it's an inverse square law, and therefore, by the fact that it's an inverse square law, that its potential energy is just an inverse. It's proportional to the inverse of the distance. And of course, we're going to need to use the definition of ellipse as a locus. So in deriving these three laws, we're going to have to develop some theory. Won't seem pretentious, but we're going to develop some basic equations of the ellipse, some basic properties of ellipse as well. And we're going to have to go over not the most, we're going to have to go over some second order differential equations, or some of the theory behind solving second order differential equations. So let's start out. And of course, we're going to start with the first law, and obviously the question that we don't even really, well, the main problem already is that we don't really know what an ellipse is. Or you may not know what an ellipse is. But an ellipse is simply a locus of 2 points. Just like a circle is a locus of 1 point, whereas the circle is a set of all points such that the distance from that point to that, from an arbitrary point to our special points that we form our locus out of is always constant. The distance is always constant, and that's simply expressed using the Pythagorean theorem, square roots of x squared plus y squared, or just the distance from between the points, and then we'll just arbitrarily choose the origin to be our point of special interest is equal to some constant r. And similarly, the ellipse is defined as the set of all points such that the ellipse is defined as for any 2 points, the ellipse is defined for any 2 points that it is a set of all points such that the distance between, we'll just call this points, we'll just denote the vector, x, call this c1, do not, plus f1, plus f2. Is always constant. So similarly, we can use Pythagorean's theorem to put this definition to find the corresponding equation that gives us the set of all points, all xy points that fits this property. So very easily we can, first of all, let's assume that our ellipse is centered at origin and that these 2 points are on the x-axis and they are respectively a distance c away from the origin of these 2 points. And using this, we can very easily write an appropriate equation. We just get is equal to some constant c. So this is our preliminary equation for the ellipse. But the problem is that we don't know what this constant is exactly. So in order to answer that question, in order to find for any ellipse what this constant should be, let's define 2 more quantities. We're going to define A, which is the semi-major axis of our ellipse. You can just think of it as when theta equals 0, A is the distance of the points on the ellipse from the origin. It's the farthest that the ellipse stretches away from the origin on the x-axis, and similarly, B represents the farthest distance that the ellipse stretches on the y-axis. And now we're just going to tinker around with this definition with 3 points that should pop out to us immediately. Specifically, these points are one of these 2 points on the x-axis, correspondingly one of these 2 points on the y-axis, and then 1 point that is above or below one of our foci. Oh yes, I forgot to mention, these 2 points, we call them foci, or the focuses of the ellipse. And so here, focus. So let's look at this point first. Let's apply our equation here. We get that, so as mentioned, this is A. So distance between our point here and the left-hand focus is simply A minus C. And distance between our points and the right-hand focus is A plus C. And this is simply 2. So that's good. We found a constant, a very nice constant. It's just two scalars multiplied by each other. No other operations, no subtraction or addition or square rooting or something. It's very nice, very simple. So we know that we can substitute our constant with 2a. Now let's look at our other points. Let's look at this point here. And apply an equation. Applying our equation here, we get that b squared plus c squared plus b squared plus c squared, that's just Pythagoras theorem, is equal to constant, which we've established, is 2a. So if we square both sides of these equations, we get 4 times b squared plus c squared equals 4 times a squared. And then very simply, this reduces to b squared plus c squared equals a squared. And this identity right here is incredibly important. We're going to be using this identity a lot. So let's put it up here in our list of established facts. There's one last point that we need to look at. We're not going to be using it for now, but we will use it in the derivation of Kepler's third law. We're going to look at this point right here, which is just simply about the focus. We're not going to be using it in this form, but I'll also leave at that because we have to introduce some other quantities to rewrite it so that it's nice. With that out of the way, let's now try to find a nicer way to express this equation. It's putting it messy right now. We have two square roots that don't combine at all. So yeah, I'll just try to find a better way to express an equation for it. So let's try moving one of these square root terms to the other side, and we'll just square. And we hope that using these identities we've established so far, we can rewrite this equation to be nicer. So what we get is we can very easily see that these terms will cancel out. So 2xc, so and 4xc equals 4a squared minus this. And now we only have one square root term now, which is very nice. So let's just move everything else to the left hand side. Let's also divide by 4 because we can, and it's not necessary. Okay, I'm going to move this over here. So let's just square the equation. We get okay, and we're just going to expand. Again, yeah, it's pretty tedious. But we have to do this, or else the proof will not be rigorous, and I feel like I'll be skipping quite a lot of steps. And, well, you know, necessarily, we do not want that necessarily. So we see again that these two terms will cancel out. Though we gotta simplify things like this. We get. Let's also move. Let's combine these two equations because, I mean, these two terms. Sorry, did I say equations? I said term. Let's combine these two terms because they both share x squared, and using actually, yes, using this identity, we're going to substitute c squared of a squared minus b squared. So we get again, looking here, we can notice, again, using this identity, that this is just negative b squared. So here we write as this. Oh yeah, again, another two more pairs of cancelled terms. So it's very nice. That's always very nice. Makes it very simple. Or simpler. So we now have this equation. This is already much simpler than our original equation up here. We just have a few more steps, and then we'll get to the equation of left that everyone is familiar with. Simply move all the terms around so that none of them are negative. Use x squared, b squared, plus a squared, y squared equals to a squared times b squared. And we just divide by a squared times b squared, we get x squared. Now we have a squared plus y squared divided by b squared is equal to 1. And this is very nice. This is actually, this should be a expected form of the equation for the ellipse in Cartesian coordinates. Because, I'll show you why, here's all of this. The reason why is that the parameterization of the circle, or parameterization, let's call it it's pretty much, yeah. It's, the unit circle is just for any circle of radius r centered at the origin. We could just say that it can be parameterized in this way. R is constant. Now the intuition for not intuition, we can notice that this should be obvious. No, sorry. If we take 2 points of this parameterization, let's say one where, that's wrong. Okay, where theta equals 0, that corresponds to the distance from the origin to the farthest. I just want a picture of a circle. And at this point, this value right here, not value, this vector corresponds to, or its magnitude corresponds to the farthest out that the circle will stretch on the x-axis, which is just r, and that makes sense because we get this. Similarly, our parameterization of pi over 2 gives us 0r, the magnitude of this. Magnitude and direction of this corresponds to how far the circle stretches on the y-axis. So if we extend this to a parameterization of the ellipse, we should roughly expect that our parameterization for ellipse, I'll call it E, I'll call it RE, value at 0 should give a vector with magnitude A that points along the x-axis because that corresponds to the semi-major axis. And we evaluate that to pi over 2. That gives us corresponding vector that corresponds to the semi-minor axis. And if we want to expect our equation to be in the form of a scalar times a trigonometric function, then we can very easily guess our parameterization to be A times cosine of theta, B times sine of theta. Because if we evaluate this at theta equals 0, we get a 0. Similarly, we get the same thing if we evaluate that pi over 2, we get 0b. And if we, oh, I have to sneeze, sorry. Okay, I don't have to sneeze for some reason anymore. If we plug that parameterization in here, so we let x equals x theta, sorry, which is this, and let y equals y theta, which is equal to sorry, I blanked out there for some reason. Sorry about that. If we plug that into here, we get a squared cosine squared a squared. Just plug it in. Okay, my handwriting is a lot worse down here on the board. And trivially, it just becomes which is always true. This is always true. It's a simple point. I don't want to say something. It's just a reformalization of Pythagorean theorem in terms of trigonometric functions. It's always true. So this equation is very nice because it corresponds very nicely to what our natural parameterization of the ellipse would be given the parameterization of the circle. This fact doesn't really matter, I just want to bring this fact up, but it's not really necessary to our proof. What is necessary to our proof, however, is that we need to note that this form of the ellipse is only valid if we are in Cartesian coordinates. Whenever we are evaluating any anything that's rotating, which our ellipse is, it's, yeah, if you patronize it and then you see how the point travels in relation to the origin, it's obviously rotating with respect to the origin. Anytime that happens, we want to express our equation. We want to express our coordinates in polar form. And that's kind of what we did with the parameterization, but it's not really, you get the rough idea. And additionally, going back to Kepler's first law, we notice that the star that the planet orbits around will be at one of the foci. So what we want to do is we want to develop another form for the equation of the ellipse that represents it in polar form, as well as representing the fact that the planet will rotate around the star, which is located at the focus. And to capture the second fact, what we want to do is we're going to shift our graph by C so that our graph is centered, so that our origin is on, our focus is on the origin, and that'll just make analysis easier when we prove Kepler's first law. So we're going to use this form of the equation for ellipse, and to get the polar form, all we're going to do is just going to substitute this in, just like we did a few minutes ago. Again, this is going to be kind of messy for a bit, but we will eventually reduce it down to a nicer form. But before I do that, I do want to introduce one quantity, a new quantity, and that will be epsilon, which we will let equal to C over A. And what this measures is this measures how far the ellipse stretches. For example, in a circle, C would be 0, A would be the radius, so epsilon would be 0. But for ellipses, it's going to be a positive value less than 1. Because if C was equal to A, then that's not an ellipse. I believe that's a parallel. We're going to call epsilon eccentricity. We can rewrite it in a nicer form, not a nicer form. We can write it in a different form so that it only depends on B. Using again that very useful identity, we can simply say this. So we defined this new value that pretty well describes our ellipse. And we will actually see later that this definition, this eccentricity alongside the semi-major axis is enough to define the ellipse in polar form. Just like here in the Cartesian form, you only need to know the semi-major axis and the semi-minor axis. So yeah, so I'm just going to put this here. Anyways, moving on, let's plug this in to here. We're going to get to want to get rid of these fractions, so let's just multiply everything by a squared times b squared. We're going to get, good. I'm going to need a lot of room for this. I don't think I have enough room. It's a bit unfortunate to say the least, I guess. Oh, sorry, that should be sine. That was the first mistake I've made. Actually, that's kind of surprising. It's been going for 30 minutes. That's the first mistake I've made, I believe. Thank God I caught it pretty quickly, or else this would not work. So let's just again use the Pythagorean identity to rewrite sine squared in terms of cosine squared. Let's also fix this. Yes. Now let's just combine some terms together. Find this one and this one. Sorry, not you, only you. Thank you. We get. You can also find these two as well. I feel like I'm missing something. Did I skip over something? That would be no. Oh yes, I have. This right here, this is all cancelled out. I forgot to include it here. I'll just add it, append it on the end. That's the second mistake. That was not a succession of those two mistakes. It's not quite long. That's a bit worrying. Anyways, so again, using that identity, we can further rewrite this as minus b4. So now it seems like we're kind of stuck. But don't worry. Don't worry. Everything's gonna be fine. I'm gonna move this over here. What we have to do is simply remove these three terms over to the right side, and you probably already see where it's going. It turns into the square of a sum. Let's rewrite this. Sorry, not the square of a sum, the square of a difference. God, I cannot speak coherently today. Well, I haven't been able to speak coherently. In general, I don't speak that coherently anyways. You see very often that this is a square, and you should be able to recognize that this is a square as well. We just have to rewrite this as this. So again, we can just square root both sides, and we get this is a very much nicer. So we're going to bring all the terms that have r in it over to the left-hand side. Yes. Sorry about that. It is not. Yes, that's fine. Okay. Now, well, here we go. We then have our equation for the elliptic polar form. Simply this, and then we can rewrite this. We can rewrite it to cancel out some more terms. And here we're going to use our definition of eccentricity. 0a cosine theta, and I said this already, but using our definition of eccentricity, this turns to theta, and then we can write this as so. And we see that this also turns into, did I say theta? I meant epsilon, sorry. This turns into epsilon squared. We can cancel out these two a's, and we get a very nice, or it looks a bit funky. It is a bit funky, but it's much nicer than whatever this was. We just get this one here. And this is a form of ellipse that we will use in our proof of Kepler's first law. I forgot to mention Kepler's first law is the most involved. The proof of Kepler's first law would be the most involved. You'll see why. Anyways, so now we have the form of the ellipse in polar coordinates. Let's put it up here. So yeah, that's pretty much everything we need to know for the ellipse. We know some very useful identities that we will continue to use. We won't use them as much, but they will pop up here and there. And we know a Cartesian form of the ellipse, a Cartesian equation for the ellipse on the Cartesian coordinates, and from that we derived the equation of the ellipse for polar coordinates, and that form is what we're going to be using to prove Kepler's first law. But before we move into talking about, actually, do I want to talk about it now or later? Okay, I will talk about the second order differential equations during the proof of Kepler's first law. So, this is the first part of the video. Oh god, 40 minutes already, Jesus. Anyways, going to end it here. I'm going to erase all this and I'm set it up for the proof of Kepler's first law. At least the first part of the proof. Okay, so with all of that stuff about ellipses out of the way, we can now start proving the first law of Kepler's three laws, which is that each planet orbits in an ellipse with the star at a focus. And here we're going to use 4 facts that I'm not going to prove, or that I've already proved. And they are the law of gravitational force, and specifically what we're going to be using is that it's an inverse square law, and so that implies that the gravitational potential energy is negative g m divided by r. Also, this should be a magnitude, not a, sorry about that. And also, secondly, that it is center-seeking. And this is quite important. Because what this implies, and I can show this, is that our system will have conservation of angular momentum. Specifically, we know that angular momentum can be expressed as theta. Oh yes, we're also going to make an assumption that we can model a system as 2 point masses, which of course isn't the case, but due to the large distances in space, we can approximate it as the physicist's favorite hobby, approximation. Actually, no, that applies to engineers, but also to. Anyways, sorry, I was trying to make a joke about stereotypes, but kind of fell flat, I guess. So anyways, angular momentum is a vector simply defined as this, and this is the time derivative of angular position, I guess. And then very clearly we can see that this is equal to the time derivative of torque. So, actually wait, let me see. I am so sorry. Oh my god, I can't believe I made that mistake. Maybe that was pretty bad. Sorry. The time to it's from this you can clearly see that the time to okay, that dot is not sure that the time derivative of angular momentum is equal to torque. So that means that if torque is 0 and torque is equal to this, the cross product between the radius, the position vector, and then whatever force is being applied on our object, which would be the gravitational force. So the time derivative of angular momentum is torque. So what is, in this case, what would be torque? Let's just, I don't need it. Let's just draw it. This is the sun. Hello, sun. How are you doing today, sun? Thank you for giving us life. Here's our planet. This is going to be our radius vector, our position vector, and our force vector is going to look like this. It's going to be parallel to the radius vector, to the position vector, because gravity is a center-seeking force. We're going to be using that fact here. And we know that the cross products of any two values, in this case, the magnitude of the cross product of any two values, in this case those values are the position vector and our force vector, is equal to the magnitude of each vector multiplied to each other times the sine of the angle between the two vectors. And since these two vectors are parallel to each other, that angle is 0, and sine of 0 is 0. So that means that torque, the magnitude of torque, is equal to 0. So that means the derivative of angular momentum is 0, and therefore angular momentum is a constant. That means it's conserved. And therefore, in this system, angular momentum is conserved. I said I would not prove this fact, but I just did. Sorry, I'm gonna take a few minutes at the very least. Oh, it's okay, so that's all we have. So we know this. Secondly, we're going to need to use this conservation of energy, and means to use our polar form of the equation of Lipps, which we've already derived. And our main strategy is we're going to use a conservation of energy to write an energy equation for our system. We're going to use and we're going to try to rewrite it in a way using the fact that angular momentum is constant in this system to try to manipulate it and to try to bring out the equation of the elliptic polar coordinates. So that's our general, that's going to be our general strategy to prove Kepler's first law. But first, there's a big problem. Our system, our equation, our polar form of our polar equation for the ellipse only works in two dimensions. It only works when our ellipse is embedded in the xy plane, or in this case, our theta plane, or just a plane given by z equals 0. And obviously, we can't just. Obviously, our planets, our star, they're arranged in three-dimensional space. Our planet is moving in three-dimensional space. We can't simply make that jump. However, using the fact that angular momentum is a constant, and specifically we can write this is equal to a constant vector. And what angular momentum measures, its magnitude measures, just how much stuff, how fast, how much stuff, the fastness in the amount of stuff rotating around some axis of rotation. And the direction of angular momentum is that axis of rotation. And all our position vectors, all of our velocity vectors for that system will be perpendicular to that axis of rotation. So that means that if angular momentum is constant, its direction of angular momentum is also constant. And that means that the axis of rotation is also constant, which means since the position vectors and the velocity vectors, in this case, those would correspond to the vectors, the kinematic vectors of our planets. Since that is true, it's always going to be on a plane, pretty much. We can find the plane in our three-dimensional coordinate system so that our planet's orbit never deviates off that plane, because angular momentum is constant in this case. And so here I'm going to make quite a unrigorous step, which is why I said that earlier that this proof isn't going to be necessarily that rigorous. We can choose our coordinate system so that when we look down on it, when we look down on the xy plane, our planet's orbit will always be contained in that plane. Like the entirety of the planet's orbit will be contained on the xy plane. Therefore, we can just treat it as a two-dimensional system, and therefore we can use our polar form of the equation of the ellipse. So we don't have to worry about that. We can just treat it as a two-dimensional system, pretty much. So let's get into the meat of the problem. We're first going to use conservation of energy, and this simply states that energy is going to always, energy of our system, we're going to treat our star like it does not have any velocity. There's no presumption, sorry. The energy system is going to be given by the kinetic energy of our planets. Plus the potential energy of our system. The kinetic energy of our planet is simply going to be given by, we're given by that, and we're going to use this fact to then say that the potential energy for a system is simply negative g times the mass of the star times mass of the planet divided by r. And so we can then rewrite this again as this. So now let's try to express everything. We need to try to express everything in this energy equation. Yes, then constant energy E is going to be a constant. So the time derivative of dt equals 0. So sorry about that again. So we're going to want to rewrite everything in this energy equation in terms of R or its derivatives. And since potential energy is already in the form part, and we just wanted to try to find another way to describe the kinetic energy. So we know that the position vector, the position of our planets is given by the function r. It's not constant here, or we can't assume it to be constant, or else it would be a circle, and we can't just say that. So I'm kind of rambling now. This is our position vector for our planets, and therefore it's given that our velocity is in is there anything missing here? Oh, I don't think that should be right. But something feels wrong. No, that should be right. Okay. That means our velocity vector is given by this. And we can see that our kinetic energy is the square of the magnitude of that velocity vector times some other constants. So now let's find the square of the magnitude of our velocity vector. And again, it's going to be an algebraic mess. We're going to just square both of these entries. We're going to add those squares together. And we're going to hope that whatever comes out of this mess is nice. Oh, this is going to go to another line. How nice. Very cool. Oh, I made another mistake. This should be... I'm not going to be like this. This should be... I do. That is good. It should be nice. No, this is just... It's just a formula for the sum of two angles for sine when those two angles are the same. That isn't relevant because as you can clearly see, these two terms are cancelled out, so we don't have to worry about that. I just want to say it because I'm kind of tired right now. I'm not really sure what I'm saying. So you get this very, very horrendous looking expression. Don't worry, it's all going to cancel out. We already see that these two terms, which are the most horrendous of all of these, cancel out, and then we can just we can combine each of these terms. We can combine this term with this term, this term with this term. We get what? Oh wait, no, it's fine. Sorry. And again, it's just that trigonometric identity, and out of that mess plops out this much nicer expression. So now we can go back to our energy equation, and we can express all the terms in terms of beta and r. So I should probably add here that this is the squared amount of velocity. So it's not confusing. Confusion. Oh my god. Did I just say Confucius? Sorry. So we get that. We don't need this anymore, so I'm going to erase it. So now our goal is to rewrite as much of this as possible in other ways. Because right now we have these derivative terms that are kind of very hard to work with. And don't worry, we can deal with these by noting. Is this right? Yeah, this should be right. By noticing again, angular momentum is defined as, in this case, since we're assuming we're treating the plane, the soft star, as 2-point masses. If we weren't, then we would have to use this expression where angular momentum is equal to rotational inertia of our system times the rate at which the system is rotating. We don't need to do that because of our assumption. Using this form, we can already rewrite this term in terms of a constant. And you'll notice how if we just square angular momentum, we get this. We can rewrite it, we can isolate this to get that. This expression right here is equal to a constant, and that constant is that. Very nice. That should be right, right? Sorry, that's not. Why did I say that's a constant? It's not a constant because there's still r in there, but it doesn't have the time derivative of theta. So that's nice. So we get now there is an issue here. Specifically, we have two terms where r is an inverse. R is in the denominator of the term. Specifically, right here and right here. Now, inverses are not nice to deal with. We want to get rid of these. And so we can do that by introducing this substitution, u equals 1 over r theta. So in doing so, I'm going to put this in established facts or established definitions. We get that we can rewrite this using our substitution as that's very messy. I should probably put it somewhere else. We don't need you anymore, so I'll erase you. Oh my god. I'm so sorry. I forgot to put in a substitute. This is hard. I can't speak either. How nice. I forgot to put in the substitution. So now, this is quite nice. There's no more inverses, however, there's still one issue, and that is this. This is the time derivative of r. It's not expressed in terms of u or the derivative of u, but we can fix this easily. We just need to see how we can rewrite the time derivative of r in terms of u. So let's just do that. We'll just take the time derivative of r, and then we'll substitute our substitution in. That was quite a redundant phrase. And then we'll just use some basic calculus differentiation rules. Sorry. And we can rewrite this again in terms. We can rewrite this part of the expression in terms of r again. It's negative r squared times this times the time derivative of theta. And you should notice again. Now we can express these two parts of the expression in terms of angular momentum. Specifically, we just get that negative r squared times time derivative of theta. It's just negative L over M. I don't think I'm making any mistakes. If I am, that would be very bad because that would probably mess up. But if I do, whatever, should be fine. So we can see that this is then just this. So using that fact, I'm going to put that over here. Time derivative of r using our expression, using our substitution is just the negation of angular momentum by m times the derivative of our substitution variable with respect to theta. I'll get with u. And now we can finally write our equation completely in terms of our substitution u. Again, we know that both these terms share L squared over M squared, so we're just going to call that out. And we're going to get this. Oops, sorry about that. So now let's exploit the fact that energy is constant in the system. We're going to take a time derivative of energy. We're going to take a time derivative of this top equation. That's what I meant to say. Yes. And we're just going to use some. Oh no, not the time derivative. I'm so sorry. I am so sorry. The derivative of energy with respect to theta. And okay, I kind of did misstate the second rule that we're going to use, but in this system as well, energy will be conserved at all points in the planet's orbits, or it's just yeah, pretty much because theta varies with time and whatever, and we're also including the kinetic energy term. If it's just potential energy term, then yeah, of course, the energy would vary with theta, but also with time. But since we're including the kinetic energy term and the potential energy term, energy is going to be constant, no matter what we're differentiating with respect to. So it's fine. How much? Oh, 26. Okay. So can you see that? Yes, you can. Okay, good. God, if I was writing this entire time, you guys couldn't see part of the board. I would have to do all of this again. That would not be fun. You rewrite this again as. Oh, that is quite a messy looking. That is a very messy looking equation. Oh god. Ooh. I'll just try it. Look. No, okay. I'll just bring it up again to here. I know it looks very confusing. I'm sorry about that. I should organize this better. We can note that we can divide the entire equation by the derivative of u with respect to theta. We get 0 equals L squared over m times the second derivative of u with respect to theta. What? Okay, oh, wait, what happened? Oh, I see. Oh, God. I am so sorry. I confused myself for a very long time. I forgot to include that u term in there, but now it's fine. You can rewrite this as so this square should not be here. And we can now you would notice that this equation is nowhere near the form of the equation for the ellipse in polar coordinates. And you are absolutely correct. Our proof is not done. This is simply the first part of the proof, where we use the energy equation to we rewrote the energy equation and we used these facts to rewrite it in this form. And this happens to be solvable. There happens to be a lot of mathematical literature out there that gives us techniques to solve this kind of equation. And that kind of equation is called a second order non-homogeneous. And that simply means that this constant that's all these terms in terms of u and its derivatives, its second derivative and its first derivative, it's non-zero. If it was zero, it would be homogeneous. This equation is called a second order non-homogeneous differential equation. And so we need to solve it. We need to solve this as second order non-homogeneous differential equation. And in order to do that, we have to, of course, talk about them and develop those techniques that would allow us to solve it in hopes that the solution for u, which we can rewrite, which would give us a solution of r theta, can be rewritten in the form of our equation for the ellipse. And that's what we're going to do. So this is the first part of Kepler's proof done. We just rewrote everything pretty much. Now we're going to develop some theory on second order differential equations so that we can complete Kepler's proof by solving this differential equation. Okay, so we want to develop some techniques, some theory to solve this differential equation. And in general, this differential equation falls under the broader category of differential equations called second order differential equations. And these differential equations, in the most general sense, there are special cases of these, which we will have to consider, is they take this form. This is called, and this most general form of a second order differential equation is called a non-homogeneous second order differential equation with non-constant coefficients. And what it means by non-homogeneous is that this right-hand side is not equal to 0. If it was equal to 0, so if this was the case, then we would call this a homogeneous, a second order homogeneous equation with non-constant coefficients. So in general, if we have two functions, let's say y1 and y2, such that they satisfy a particular differential equation, then the general solution to this differential equation is just a linear combination of these two particular solutions. Now, you might be asking, do we have to, besides the condition that both of these functions are particular solutions to a differential equation, do we have to, or do there exist any other conditions that have to be satisfied so that this this general solution can work out, and that when you're given a set of boundary values, or initial values, that it then gives us well-defined coefficients? And let's see. And the answer is yes, there does exist one more condition. Specifically, if we have I already made a mistake, sorry. So I said we would we're not actually okay. So this is the general form of differential equation of the second order differential equation, but for now we're only going to consider homogeneous second order differential equations. Sorry about that. Got that wrong. But anyways, if we do have a second order homogeneous differential equation, so I'll just write this again over here. Actually, no. Sorry. Actually, I do want to continue. I do want to continue talking about non-homogeneous differential equations, but I'll leave this condition right here. What I was just talking about there being another condition for our general solution to be written in terms of these pair of particular solutions. I'll come back to that later. First, I still want to continue talking about non-homogeneous differential equations. So for each non-homogeneous differential equation, we will define an additional equation called the complementary equation, which is just the homogeneous equivalence of this non-homogeneous differential equation. And that is simply, you pretty much preserve the entire right side, but, I mean the entire left side, but you make the right side equal to 0, so that it is homogeneous. And so there is a very nice theorem that exists between non-homogeneous differential equations and their corresponding complementary equation. And that is, if we have two particular solutions to our non-homogeneous differential equation, so say capital Y1 and capital Y2, then the solution y1 minus y2, and it could also be y2 minus y1, it doesn't matter, is then a solution to this complementary differential equation. And in general, the general solution to a homogeneous differential equation will be in this form. And we'll come back to this later, but just take it for granted for now. So we can write it. So this difference of the particular solutions to the non-homogeneous differential equation will be a solution to our complementary equation. And a particular solution can be written as parts, this is kind of unrigorous, as parts of the general solution. So we can then write that this is the case. For any two functions, little y1 and little y2, that are particular solutions to this complementary equation. And there actually does exist another condition that requires a solution to, requires this theorem to work out, specifically for us to be able to make this equivalent statement. And that is that y1 and y2 are a fundamental set of solutions. But this fact, we will return to this fact when we go back here to discuss a bit more of the theory behind complementary, or behind solutions to homogeneous differential equations. So anyways, so let's now prove this theorem, and this is a very simple proof. We'll just plug in y1 and y2 back into this complementary equation. So what we get is I'm running out of room. This is very sad. I'll just put this equals 0 on this side. And then we can just group all the terms that have y1 in them together, and similarly group all the terms that have y2 with them together, and we get this once we apply the derivative operator to all of them. And then just rewrite it as sorry, we need to prove that this is a solution to the complementary equation. So this 0 should not be there in the first place. Sorry. But anyways, and of course now we're going to just use the fact that each of these particular capital particular solutions are solutions to the non-homogeneous differential equation. So we can just substitute these larger expressions for just gt. And we get gt minus gt, which is equal to 0. And that proves that this difference of these two particular solutions is a solution to our complementary equation. And therefore, if we have small y1 and small y2 are nice enough, if they're a fundamental set of solutions, we'll talk about it later, I always said that, then we can write this. And these two functions right here, big Y1 and big Y2, they can be any solution to our non-homogeneous differential equation. Specifically, we can set one of them to be our general solution. So if we set just, I don't know, Y1 to be our general solution to our differential equation, to a non-homogeneous differential equation, we set Y2 to be just any particular solution to our non-homogeneous differential equation, and we'll call this P, y subscript P. Then it will equal to this linear combination. And for now, let's just denote this linear combination as yct, the general solution to our complementary equation, y subscript c. And then we can rewrite our general solution to the non-homogeneous differential equation as just yct plus ypt. So this is actually really good, because what this tells us is that in order for us to find a general solution to our non-homogeneous differential equation, all we need to do is we just need to find the general form of the corresponding complementary equation, and that's not hard. We'll show later that we can do that. Usually, we can do it quite easily, and then we need to find a particular solution for our non-homogeneous differential equation. And usually, to find our particular solution, we will use two techniques. We will use either the method of undetermined coefficients, or the variation of parameters. And both of these methods are quite complex, they're maybe not quite complex, but to explain them and to give proper examples for them would be quite we would have to spend a lot of time on that. And in retrospect, it is trivially easy to find a particular solution to the non-homogeneous differential equation that we do want to solve, which is this equation right here. And looking at it, you can probably already guess what it is, but just in general, for more complex second order non-homogeneous differential equations, you would have to use one of these two methods. But I'm not going to go into it now because it's not really necessary for our proof. So that's in general is how we are going to find our general solution to our non-homogeneous differential equation. So, and as I've already stated, to find a particular solution for Kepler's first differential equation for Kepler's first law, well, it will be trivially easy. So we only need to focus now on finding the general solution to the complementary equation, the general solution to homogeneous second order homogeneous differential equations. So we're going to talk about that now. So when we do talk about this, we'll first have to consider a subclass of homogeneous differential equations. We're going to have to consider homogeneous differential equations with constant coefficients. So first, let's do an example. Let's take a very simple homogeneous differential equation, which we'll say is just this. So we're going to have to ask ourselves, does there exist any function such as its second derivative is 4 times as large as its, sorry, I just realized you could see this list of examples. Sorry, my memory isn't too great, so I just put them up there in case I forgot, but we're actually only going to use one of those. Because this one, I was originally going to use this one for demonstration of method of undetermined coefficients, but like I said, we don't have time for that, so I'm not going to. And this one was also going to be used to explain a subtle detail about the method of undetermined coefficients. I might use this one, I'm not sure about, but really, for now, let's just consider this example. So going back to the point, well, obviously it can't be a polynomial function, because if it was, then each, just the first derivative would be what was it called again? It was like, I forgot what it was called. You know, like the biggest power in the first derivative would be 1 less, and the biggest power in the second derivative would be 2 less. So obviously you can't combine those to get 0. You would have a leftover larger power. So like x cube or x squared, you know, whatever. So then what about the trigonometric functions like sine and cosine? In this case, whenever you take the whenever you take the second derivative of these, you do in fact get back that function. But the problem is that due to the fact that the derivative of sine is equal to negative, due to the fact that the derivative of cosine is equal to negative sine, these will be negative. Sorry, I shouldn't, this not equal when we apply the second derivative, then we get this. So obviously a negative minus a negative, well, two negatives won't cancel out. So this will not work either. But there in fact does exist a function that suits this differential equation, and that is the exponential function. So let's assume that there exists a solution as in the form of a exponential function. Let's plug it back into here to see what r would have to be. So you would simply get r, differentiating twice, you get r squared times e times the exponential function, and you just minus 4 times the exponential function. Then we can take out the exponential function, because the exponential function, if the entries to it are always real, it will never equal 0. So we get r squared minus 4 equals 0. This is just a quadratic equation, and very obviously the solutions are r1 equals 2 and r2 equals negative 2. So therefore our general solution to this differential equation will be some linear combination of this differential equation of these two exponential functions, which would be e to the negative 2t and e to the 2t. So this is our general solution to this particular differential equation. And from there, you can determine what these coefficients are. You can only determine what these coefficients are. Specifically, when you determine what these coefficients are, you are finding a particular solution for your situation. And you can only do that when you're given a set of boundary values, which, for example, could be maybe the solution at 0 is equal to 1, and the derivative of the solution at 0 is equal to 2. And it really could be any pair of input and output. It could actually be like an inequality, like maybe instead of y0 equals to 1, we have the first derivative at 0 equals 2. And the second derivative at 0 is greater than or equal to 0. It could be anything. But specifically, to find what your coefficients would be for a particular solution, you would have to have at least 2 boundary values that you would then just plug in everything. You just use the general solution, the general form of the solution, to then plug it into those boundary values, and then you would get a system of equations, and you could then solve for that system of equations for your 2 undetermined coefficients. But anyways, that's besides the point. See, if I want to talk about this, I wonder if this will work. Yes, okay, I think this will work. So in general, to find. Oh yes, I forgot to mention. I should have mentioned that at the very start. But throughout this entire thing, we're going to use a very useful property for differential equations, which is called linearity, or equivalent superposition. Which is that for any differential equation, if you have two solutions, y1 and y2, then any linear combination of that differential equation of those two solutions is also a solution to a differential equation. We're going to be using this law, and this just has to do with the fact that the derivative operator is linear. And there do exist nonlinear differential equations, which are very scary to think about. But of course, we're not going to talk about this here. Anyways, I talk about there existing another condition for our two particular solutions, so that their linear combination does give the general form of our solution to the homogeneous differential equation. So we're going to look at an example of how there does exist a second condition. Specifically, we're going to look at this differential equation. But before I talk about this, I actually want to go over, in general, actually, yeah, so before we go on, in our solution to this differential equation, what we did is that we assumed that there exists a particular solution that is an exponential function. We assumed that this function is a solution. And then using that assumption, and we then plugged we plugged this exponential function into a differential equation. So in general, for homogeneous equations of like this form, when you plug this exponential function in, you would get again, you just cross out these you just get rid of the exponentials, and you just get a corresponding differential equation, a corresponding quadratic equation. And we actually give this equation a name. We call this the characteristic polynomial of a homogeneous differential equation. And then just solve for this. And usually, depending on if these roots are if you have two real roots or just one real root, when the discriminant is 0, or two complex roots, you have different general forms to the homogeneous differential equation. And we'll talk about that later. We'll derive all the general forms later. But it's important to note that for any homogeneous differential equation with constant coefficients, really the general solution only matters on the corresponding characteristic polynomial. Just want to get that out of the way, because I think now is the best time to talk about that. But anyways, let's get back to this. Let's consider the next example, which is, as I said previously, just this. So this differential equation's characteristic polynomial will be r squared plus 2r plus 1 plus 0. It's just r plus 1 squared. So this gives us only one root, -1. So you might think this shouldn't be a problem. This should just mean that our general solution is then just C1 . So it's this. And therefore, two arbitrary constants are being added together just equal another arbitrary constant. So this should work, right? No, it does not work. Let's consider, specifically when we're trying to find a particular solution, this does not work. Let's consider, for example, the boundary value y at 0 equals like 1, and the derivative of y at 0 equals like maybe -1. Actually, would that work? I think it does. So then what you get, I'll just replace this C with an A. I think it will look better. Yeah, that's y0 goes to A, which equals to 1. It's similarly, that's, of course, the derivative of this solution, of this general solution is just negative. Sorry, these r's should be 1. I forgot that. Yeah, these r's are 1. So that, therefore, the derivative of the general solution is just negative a times exponential function. So this value at 0 is just negative a. Yeah, okay, so, yeah, sorry. This doesn't, I need to choose a difference. Yeah. Let's go to, that's so embarrassing. I'm so sorry. You get this. You get this set of, you get this set of this system of equations. And this tells you that a equals 1. But also that a equals negative 2. And this is clearly a contradiction. And so this means that these two pairs of functions, this pair of functions does not work. The condition that any two functions that are particular solutions to our differential equation is not enough. We need another, there exists some other condition as demonstrated by this example. And we're going to get into that now. Specifically, let's see. Does this, which, I think this only, okay. So this should work for homogeneous differential equations with non-constant coefficients. So we can work on this. If we have this differential equation and we have some boundary values. Let's say we have the particular solution evaluated at 0 equals some arbitrary number, and the derivative of the particular solution evaluated at 0 equals another particular number. And let's say we have two particular solutions to this differential equation, y1 and y2. Then let's assume that these are nice enough to form a good general solution. That's their linear combination gives a general solution to our differential equation. So now let's plug that in to our boundary values. And we will, yes, then we will get C1 we get this system of equations. Sorry, there's someone. Okay. So anyways, so we get this system of equations with two variables in two equations. So we can model this as a square matrix times a vector that contains our unknowns equaling these constants on the right-hand side. And this will just be C1, oops, sorry, no, not that. Y10, Y2, is this right? Sorry. Yeah, this our boundary values, we shouldn't restrict our boundary values to just be at 0. We can allow it to be at any arbitrary constant, which we'll call t0. So sorry, that's my mistake. My memory's not that great, so anyways, we can model this system of equations as this linear algebra equality. And so we now want to ask ourselves, what is C1 and what is C2? And to find solutions to C1 and C2 from this matrix times vector equals the vector equation, we're going to have to use something called Cramer's rule. I don't think I have enough room to explain it. That is very unfortunate. I'm going to erase this, but I don't think we need it anyway. So this is Cramer's rule. And basically, what Cramer's rule says that you have if you have a similar solution here, but in general, it can just be any square matrix of n by n dimension being multiplied to, so I'll let this be x instead, to some vector of unknown variables. And this gives you another vector of known quantity. And we'll denote this matrix as A, this vector as x, and this unknown vector as x, and this known vector as y. And Cramer's rule says that for each x, and we'll just say it's arbitrary subscript sorry, not n, that's a dimension size. Then the solution to x is then given by the discriminants of a modification of our matrix A divided by the discriminant of A itself. And this modified matrix is just, if we denote each of these column vectors in matrix A as A1, A2, A3, etc., then AM is just simply A1. It's just the same thing as matrix A, except for at the nth column vector, you replace AM with Y. And that's just AM. So that's Cramer's rule. And the discriminants is just, it's just an operation you can perform on any matrix. And on 2 by 2 matrices and 3 by 3 matrices, the discriminant corresponds to either the area or the volume of the parallelogram or pipette formed by the vectors that make up the matrix, which is really it is quite an unrigorous description, but whatever. Anyways, do I have enough room? I kind of do not. That is very sad. Anyways, so applying Cramer's rule to to the equation that we are concerned with, we then get that C1 will be equal to the discriminant of and this is just a scalar over a scalar. It might look like a vector, but it may look like a matrix, but it's not. It may look like a matrix divided by a matrix, which isn't well defined, but it's not. It's just the discriminant of a matrix, which gives a scalar. And similarly, C2 is going to be given by So I'm writing very low, and it's going to be very unneat. But it's pretty much the same thing to this, where you, except for you just change, you just replace the second column vector with y instead of the first column vector. So that's a matrix. That should not be a matrix. That should be a discriminant. And so we'll notice that our coefficients C1 and C2 will only be well defined if I'm just going to erase all of this up here. I could also use that. I could also use that. I could use this part of the board as well, but I've already erased it, so it doesn't matter. I guess these. Anyways. That means when we are given a set of boundary values, and we then find our particular solution from our general solution. That does mean then that C1, that our coefficients, will only be defined if we try to find a particular solution from a general solution that is a linear combination of two particular solutions of the differential equation. We can only find our particular solution if this discriminant if this discriminant is equal to 0 for all t. And we will denote this discriminant to be, we will call this the Wronskian. And if the Wronskian of our two solutions does equal, sorry, this should not be equal to 0, that should be not equal to 0. Sorry about that. If it does not equal to 0 for all t, then we call y1 and y2 a fundamental set of solutions. And if hello, sorry, I'm recording something. So, okay, just make sure, Okay. So if y1 and y2 are fundamental set of solutions, then the linear combination of them will then give us a form, will give a form for our general solution. So anyways, that's our additional condition that we have to put on so that our general solution can give us well-defined particular solutions. So anyways, with that out of the way, we can now find the general form for all three cases of our characteristic polynomial. Specifically, we have three different scenarios. We have that the solutions to our characteristic equation gives us two real values, or it gives us one real value that happens to the discriminant 0, or it gives us two complex numbers. So first we're going to start off with the easiest case, which is when both of the solutions are just real values. So, and this is honestly very trivial. This is just y equals c1 r1t. If we have, this is our characteristic equation, and solving this gives y1, r1, r2, where R1 and R2 are part of the real numbers, and R1, R2, and R1 does not equal R2, then we have this. That is just the general solution for this case. It's very simple. And the Watskin of these two exponentials will never equal 0 for any t. That's guaranteed, which is why we can write the general solution as this. So that's very simple. Next, let's consider when we have two complex solutions. And just due to the nature of the quadratic formula, when that does happen, we can write our two solutions to be of this form. And here we're going to use that property that I discussed earlier, the property of linearity, or slash the property of superposition. And specifically, we know from this that we have two particular solutions, which is just these two, and plugging their expanded representations into this equation, and then using some properties of the exponentiation, we then just get this. What the problem is that we can't use these two solutions to create our general solution because they're both complex values. They're not real, and that doesn't make any sense. So we're going to use our property of superposition to use these two complex solutions to find two other real solutions that are fundamental sets that we can then use to form our general solution. Let's see, how does it go? Well, we can use Euler's identity, or not identity, Euler's formula. Let's say and then we just use some trigonometric identities. We can just put it like this. So automatically we see one way to combine these two complex solutions to get one real solution. We just add them to each other. So y1 plus y2, we'll say we'll define another sure solution, y substitute 3, which is just a sum of these two. And that will just give us this. And I am so sorry, there should be a t in all of these entries, and I forgot to put that. Oh my god. That is such a huge mistake. I can't believe it took me that long to catch it. Sorry. So, anyways, since I fixed that, this solution is real, so we can use it. Now we just have to find another one, and that will be, we can divide each of these solutions by I. And then how do we divide these? We would have to subtract them. That would give us so by dividing by I, we make this sign term real. And by subtracting these two, by subtracting y1 and y2, we would then cancel out this cosine term. And we would just get this value right here. So it then turns out that in general, general solution is just given by a linear combination of these two this should have a t, this should have a t. It'll just be given by a just, oh god, linear combination, I said this so many times. Linear combination of these two, of y3, y4, and a and b are arbitrary constants. Scaling arbitrary constant gives you another arbitrary constant, so we can just simplify this as this right here. So in the case that the solution, so this marker is running out. In the case that our characters, this pen is actually running out. I need to find a new pen. I mean, new marker. In the case, this is marker good. Yes, thank God. Okay. And in the case that the solution to our characteristic polynomial gives us two complex values, this is the general solution. And we'll actually we will actually prove that these two, that y3 and y4, I accidentally erased it, but sorry, that y3 and y4 are in fact a fundamental set. So we'll just go over that. Now we'll have I might have forgotten how to do this, which might be that would be not great, you know. So there's not enough room to do this. So our want scheme of y3 and y4 is just equal to this discriminant. And we get, we have some fairly messy algebra. Oh, sorry, oh god, oh no. That is, yes. I can expand, so I can do this. Sorry, I'm modeling to myself. I made a tiny mistake. And then here would be the same thing. Oh, this is not really what the heck? Oh no. Oh, minus, yes, that should be a plus, sorry. Okay, this works. So, these two terms will cancel out, of course, and we get, so this should not be 2, and it should just, So we just get this, and we know that this equals 1, so we get that the Wronskian of these two, of y3 and y2, is just an exponential function, a real exponential function with real values, and with real entries, sorry, and we know that that never equals 0. So y3 and y4 are indeed a fundamental set of solutions. I'll just put this over here. So now we have to talk about the final case. That is the case where we only get one real solution, or when the discriminant is equal to 0. And in this case, we will have that for this, our characteristic polynomial will be this, and therefore, since discriminant equals 0, the only solution for R is negative b over 2a, of course. So from here, we only have one particular solution, and we need to find another particular solution to complete our fundamental pair, our fundamental set of solutions. And to do this, we're going to use a technique called reduction of order. And usually you use reduction of order to find solutions to homogeneous differential equations, second order homogeneous differential equations that have non-constant coefficients. But we can also apply it here. And pretty much what reduction of order what it does is that it assumes that there exists another solution to your differential equation that is simply a solution that you already know times some function. So in that case, so that would be v times e to the negative b to a to just the exponential function to y1. And so what you have to do is we have to find v. So let's now do that. We're just going to plug y2 back into our differential equation. We get, yes, that's right. Okay, so first to do this, let's just find the derivatives of y2. So the first derivative will just be second derivative will be and these two terms right here will just combine into negative b over a. So let's just combine now we just plug it into here. We get move this down. We get let's see. I feel oh god. And we can see that these two terms will cancel out. So we can combine these two terms as well. In fact, we can combine these two terms. You probably can see that. And then we can get oh god, oh, there should be C here, yes, okay. C minus oh, and of course we require that all of this equals to 0 because we need to try to find a solution, another solution using reduction of order. All of this equals to 0. So now we can remove the exponential function, and we just get this. And you'll notice that b squared minus 4ac, if you divide that by negative 4a, you get exactly this. And a will always be a will be non-zero, because if it was zero, then we wouldn't have a second order differential equation. We would have a first order differential equation. So that means that this is just the discriminant scale. And you know that the discriminant is zero because we only get one real solution for our characteristic polynomial. So you get that this is the case, and we want this to equal to zero. So we have to have that for y2 to be a solution, we need that a times v times the second derivative of v has to equal 0. And we know that a can't be 0, so that means the second derivative of v always has to equal 0, which means that the first derivative of v has to equal some constant, and that v itself has to be some linear function. So v just in general are equal to like ct plus k or something like that. So we know that y1 equals this, and y2 equals ct plus k times exponential. So we get that our general solution is just an arbitrary linear combination of these two. I'll let this equal a. I actually let this equal. I'll let this equal a. I'll let this equal b. And we get And so this is just some combination of arbitrary constants. And this is also a combination of arbitrary constants. And whenever that happens, you can just replace that with another arbitrary constant. So you get that the general solution for this scenario is this. So now we have developed enough theory to finally approach our second order differential equation. And so the complementary equation for this differential equation will simply be this, and the characteristic polynomial for this complementary equation will be, remember, what we need to do is that we need to find the general solution for a complementary solution, which will be just right here. We can just use what we derived earlier pretty much. And then we need to use, find a particular solution. And actually, let's start to find a particular solution. It's going to be very easy. It's literally just going to be this constant on the right-hand side. And I'm not going to verify for you that this is a particular solution because it's trivial. So anyways, our general solution will be this right here. I'll just say it. Why? It's a constant. You take the derivative, it's going to be 0. So just it equals to itself. Plug this in, and this will go to 0. this will just be this, and therefore the equality is satisfied. But anyways, so this is the general form. This is the general solution. The form of our general solution. We need to find YCT. And so finding YCT, we find that our corresponding characteristic polynomial is r squared plus 1 equals 0. And this gives that r1 equals 0 plus I, and r2 equals 0 minus I. And so going back to here, our general solution to our complementary equation will be of this form. So here that's y equals yc, small yc. I should be using u, not y. Sorry, we're solving the differential equation in terms of u, not y. I am so sorry. Yep. We got that's uct equals c1. Actually, I'll just replace it with a 0 cosine t plus b sine t. If it is e to the 0 is just 1. So we'll just get that this is our general solution to our complementary equation, and therefore that's the general solution for u. It's going to be is just going to be this right here. So now we need to, oh god, this is so loud, sorry. So now we need to find some boundary values so that we can find a particular solution. Specifically, what we can do is that we can set, so we don't know that, we still don't know if it's ellipse or not, so we'll just have like an arbitrary orbit or something. And so to find our boundary values, we can just take our arbitrary orbits, which we don't know is an ellipse yet, and we can just set it so that at theta equals 0, we have that r is a minimum. But the distance of the planets from the star is just a minimum, pretty much. And therefore, u at theta equals 0 will be a maximum, because u is just the inverse of r. So that's mathematically described by this set of so maximum should be actually it's 0, which yes, that should be right. Should be. This requirements, and we can do this because we can just choose our coordinate system by just rotating it, so that is the case. I used this argument earlier with arguing that we can reduce our three-dimensional problem to a two-dimensional problem. So I'm just going to use it again. I don't care. So we get these set of boundary values. It's an inequality. It's an equality and an inequality. So plugging that in, we have to first find. Okay, so it just stopped recording for some reason. That's so sad. Okay, so anyways, again, yes, we have this, and we have this, and then we'll just compute. I'm not going to do all the work again. Actually, I want to do the work again. We get that this is the case. I mean, it wasn't that long. It was only like, it wasn't that much time lost. It was like 5 minutes, I think, but whatever. I can't believe it just stopped recording for no reason. That was so dumb. That was so peculiar. So we get that the first derivative of our general solution is this, and our second derivative of our general solution is this. And so plugging in theta equals 0, we get that we require b equals 0 and require negative a to be less than 0. So this means that which is also equivalent to a is greater than 0. So this means that in our particular solution, we will have no sign term, and this will be scaled by a positive value. A will be positive. So, anyways, I already have our work up here. Using the fact that u is just inverse of r. R is then just this right here, and then we can multiply both the numerator and denominator by the inverse of this mess of constants, and we get that r equals to this. And then letting the eccentricity equals to this mess of constants. And this is well defined. We can do this because a is positive. All these values are positive, and so the eccentricity will always be well defined. If a was negative, though, we wouldn't be able to say this, which is why we're very thankful that a does turn out to be positive. And if equivalently, actually, I think requiring r to be a maximum doesn't actually require that the second derivative of u has to be strictly negative. I think it actually just means that it has to be less than or equal to 0. But if a equals 0, then our eccentricity equals to 0. And that's fine. That's just a circle. So even in that case, we're a-okay. But anyways, putting in these substitutions in here, we just get the equation for an ellipse in polar coordinates. That's very good, because that means that we've proved it. We've proved Kepler's first law. It took us like 2 hours, but it's fine. Very good. So now we're going to prove Kepler's second law and Kepler's third law, and these laws are they're related to each other. You can only prove the most general form of Kepler's third law using results from Kepler's second law. So we're going to now go over that, I guess. So I promise it won't take nearly as long. At most, maybe these two laws combined will take like an hour. So see ya then. Okay, so now we're going to prove Kepler's second law and Kepler's third law. Kepler's second law is really, really easy. And it just says that if the time that the planet orbits is always constant, the amount of area that it sweeps out is going to also be constant. So we can easily prove this. The area that the planet will sweep out is going to be this. I could prove this, but I don't really want to. This is a standard result in like AP calculus. And now we're going to make the substitution. Let's see, what was this? Actually. Oh, what was this? We're going to make the substitution theta equals theta t. And so that's d theta is just the time derivative of theta and dt. And of course, so performing the substitution, we of course have to change our boundary values on the integral, and we simply get this. And what do you know? What does this look like? It's r squared times angular velocity. That's just r divided by 2m. And sorry, this should be in terms of T1 and T1 and T2, where theta 2, theta 1 equals this, and theta 2 equals that. So let's get this equals to this. Well, of course, I will put area here just to clarify things. This, and then if we let time interval equals to t with, t to t1, we get this. So we see that area only depends on, the only variable in this equation is the time interval. So if the time interval is always constant, then the area swept out will always be constant. And that's pretty much it. That's Kepler's second law. Now, we're going to prove Kepler's third law. And Kepler's third law simply states that the square of the period of orbits is proportional to the cube of the semi-major axis of our orbits. And this really can be just thought of as a corollary to Kepler's second law. Because, as I said before, this is true. So if we let the time interval equal the period of the orbit, we then get this, where this is just the area of the ellipse, and we have the period in here. So then we can square this, and we get this. So we already have our t squared. We just need to somehow manipulate this side of the equation such that it drops out a cubed. And so to do that, the most obvious answer to figure out if this can happen, if this works, is what exactly is the area of an ellipse? So let's prove it now. So to prove this, to find the area of ellipse, we're going to use the Cartesian definition, Cartesian equation. We can see that our ellipse is symmetrical, and so this area equals to this area. So really to find the, in order to find the area of the ellipse, what we will need to do, if we rewrite this equation in terms of y as a function, we will get this. So really, since our ellipse is symmetrical, what we just need to do is we just need to determine what this integral is. We need to find the area of this half, and we need to multiply that by 2. And we just get 2 times integral of y from -8a, which is just this integral right here. To solve this integral is a bit hard. You will have to use something called trigonometric substitution. Pretty much it just capitalizes on the Pythagorean identities. Specifically, we're going to use this identity. I'm going to rewrite it in terms of, let's see, I want it to be, yes, let's do we can rewrite that in terms of this, we can rewrite like this. Oh, did I do something wrong? I think no, it's fine, sorry, no, everything is fine, sorry. So pretty much in trigonometric substitution, we're just going to exploit this fact. And how we do that is we introduce this substitution, a equals x equals a times sine of x. So this will turn our integral into So it'll be, our boundaries will change to pi over 2 and negative pi over 2. And we'll get in here. And d of x will equal to a of cosine of x. Oh my god, okay, sorry, it should be x equals a times sine of theta. We don't want to say x equals a times sine of x. That is completely nonsensical. So we want to use, we'll just find in terms of theta. I mean, like, I guess we could just do it. We could just do that because, in the end, theta is just a dummy variable. So our differential will then become this, a times cosine of theta times d theta. So our integral turns into this. And now we're going to export this identity here. We can just say this integral is in and now we're going to use now we're going to use this trigonometric identity. Oh god, no, this is, wait, this is, oh god, no, sorry. This will turn into cosine, not sine. So you get cosine squared. So now we're going to use this identity. Cosine squared equals sine squared minus cosine squared. Wait, is that right? It's cosine squared. No, oh my god, I can't. Sorry, we're going to use that identity cosine times 2 theta equals cosine squared minus sine squared. That should be correct. So we can rewrite this using again this identity. We can rewrite it as, let's see. Rewrite it as 2 cosine theta, 2 times cosine squared minus 1. So we get that 2 times cosine squared equals cosine 2 theta plus 1. So this integral can then just become, using that trigonometric identity, so you get 1/2 AB sine of 2 theta plus AB theta from pi over 2 to negative pi over 2. Okay. Sine. So when we evaluate this, we get we get 2 terms with sine of pi. We get terms of sine of pi and sine of negative pi, and those are simply equal to 0. Yes, wait, yes. Yes. So this term right here will contribute nothing to the overall integral. We only have to worry about this term, and computing it, we get pi over 2 AB minus negative pi over 2 AB. And this is simply pi times AB. This is a very intuitive result, just like pi r squared is equal to pi times r times r. It's just pi times A times B. Where you can think of the vertical r and, sorry, the vertical r, the horizontal r as B and A. So we now know the area of the ellipse. We can plug that back into this equation here. This should be squared. I am so sorry. I am making a lot of mistakes. Anyways, we now know that the area of the ellipse equals to pi times a times g. So pi times the semi-major axis times the semi-minor axis. And so we can rewrite this as this. And so now we're going to use, I'll just rederive the identity. We have, it's been like 2 hours since we've last seen it. So I'll just rederive it here. We're going to look at this point on ellipse here. And looking at that point, we can then say, since this distance is 2c, and we're going to define this distance here to be r0. We can then say that r0 plus square root of plus this distance d, which is using Pythagorean theorem, which was 4 times c squared plus r0 squared is equal to 2a. And then we can move r0 on the left side to the right side. And we get 2a minus r0. We can just square all of this, so we get this. We can see that these terms cancel, and we can combine these terms. And again, using this identity up here, we see that c squared minus c squared minus a squared is just negative b squared. This should be negative is equal to this. We're going to move this up here. So we simply get that b squared we get that b squared is equal to 1/2 times a times this defined r0, which will be unique for each ellipse. R0 is just a distance. It's just the distance of the points above or below one of the foci. The point on the ellipse, that is. So this should be right, yes. And so plugging this into here, we just get just get this. Where is my... Oh, I forgot the period. Sorry about that. So we can just rewrite this as and everything here is a constant. And so this means that the period squared is proportional to the semi-major axis cubed. And so that's that. That's all of Kepler's laws proved. As I told you, the majority of the meat of this video, or depending on how I edit these videos, is Kepler's first law, which is quite a bit, yeah, looking at it, Kepler's first law is quite a bit more, the statement of it is a lot more abstract, I guess, or it just seems harder to prove, so it's expected, I guess, but we've done it. Yep. So, thanks for watching. Hopefully you learned something. I certainly have learned a lot through this process. But yeah, anyways, thanks for watching. Have a good rest of your day. I am very sorry. I forgot to say one thing about Kepler's third law. So the problem with this is that we just kind of introduced R0. We don't have an expression for what R0 is. But using our what we derived in Kepler's first law, we know. Oh God. I think I remember it. It should be. We know that the equation for the ellipse of the planet's orbits. The equation for the planet's elliptical orbits is should be this. And remember how we defined our coordinate system. We defined our coordinate system so that the origin is at one of the foci. So therefore, we can actually use this equation right here to find out what R0 is. R0 is simply R evaluated at theta equals pi over 2. Because of how we defined our coordinate system. Can you see everything? I think you can, so it should be fine. So we actually can find what R0 is. I'll just erase all this up here. We just need to find what R pi over 2 is. That's very easy. We just plug this into here. And we know that's cosine of pi over 2 is just 0. So that means that R evaluated at theta equals pi over 2 is just this. And so now let's plug this into here, and we get just get this. And first of all, it's much nicer looking, and it also captures one other detail of Kepler's third law that I actually didn't include in my statements, which is that for any planets that has for any two planets whose ellipses have the same semi-major axis around their parent star, they should have the same period. And since the constant of proportionality relies only on G and M, if they are in the same system, the same star system, and if two planets are in the same star system, and they have the same semi-major axis, then their period should be the same. And since M is the mass of our star and G is a universal constant, this statement captures the fact. So I just wanted to include this because this statement is not quite complete. So anyways, thanks for watching. So yeah, have a good rest of your day.